Hello students, welcome to my lecture Chemical Synthesis of Polypeptides. We have seen in a previous lecture how polypeptides look like, what the structure of polypeptide is. We have learned that they consist of alpha amino acids that are connected via peptide bonds. In the lecture today, I would like to show you how we connect individual amino acids in a sequence-specific manner by chemical means. Before we can do that, we need to solve two problems. The first problem is that amino acids are bifunctional molecules, as the name says. They have an amine group at the C-alpha carbon and they have a carboxylic acid at the C-alpha carbon. And when we want to connect, for example, the blue amino acid with the red one, we only want to have them connected in one way. As the way shown here, it is the blue amino acid should form the N-terminus and the red amino acid should form the C-terminus. So that means we don't want to have a combination red forming N-terminal amino acid and blue forming the C-terminal. So we need to connect the amino acids together in a specific way. And how can we do that? This is realized by protecting the groups that should not undergo the peptide bond and leave one carboxylic acid free and one amine free, so that the two amino acids can be connected in a specific way. So this was the topic of the protective groups, and we have here protective groups for the amines, we have protective groups for the carboxylic acid unit, and not to forget, and that's very difficult to anticipate from this slide, we also need to protect the side chains of the amino acids that carry different functional groups that potentially can be competition to the amine and carboxylic acid groups in the synthesis. So they also need to be protected. The second problem that we need to solve is that we need to activate the carboxylic acid in a specific way so that they can react, that the carboxylic acid groups can react with the amino groups. When you just mix two amino acids that are properly protected without activating the carboxylic acid groups, you just have a migration of the proton from the carboxylic acid to the amine, so form an amine ammonium cation. So then you just form the salt, but you do not form a covalent bond between the two amino acids. So we need to activate the carboxylic acid as indicated here on the slide. We render the carboxylic acid more reactive via introducing the functionality X, and then the properly protected amino acids can react with each other to form the dipeptide, and then the dipeptide can be either continued to be extended on the amine or can be continued to be extended at the side of the carboxylic acid. So during the synthesis of peptides, there is one additional problem that needs to be solved, and this is the problem of racemization. Racemization is a process that happens, and in the process of racemization, the stereo configuration at the C-alpha carbon of the activated carboxylic acid gets changed. That means we don't have L amino acids, but out of the activated L amino acid, we form the corresponding enantiomer, which is the R amino acid usually. On the next slide, we see the mechanism of racemization that is usually valid for activated and protected carboxylic amino acids. The second possibility is shown here in the scheme. In this case, the direct alpha hydrogen abstraction is mentioned. When a base directly removes the hydrogen at the C-alpha position, you form a sp2 hybridized carbon, and reprotonation can now take place from two sides, from top or from bottom, and via this you change the you generate a racemate. That means that 50% of the L and 50% of the S enantiomer are then present in your reaction mixture. So let's move now and have a look at the intermediates that can form, which induce the racemization. What happens is that oxazolone 100 is formed. This happens by a mechanism where the activated carboxylic acid forms a 5-membered ring, and this 5-membered ring with the number L100 shown in the center of the top row. This compound can undergo ketoenol tautomerism. That means we have a deprotonation takes place at C-alpha, where the R2 is, and the proton migrates to the carbonyl group, now forming in compound 102 a hydroxy group. And once this tautomer is formed, then there are again two possibilities how reprotonation can take place of the C-alpha, and that leads to the D isomer and to the L isomer, meaning that we form a racemate, and meaning that we form the wrong stereoisomer that gets then incorporated in our peptide sequence, and this leads to functional loss of our peptide material. The solution to this problem was that the finding was made that when instead of amines, simple amides as protective group, uracenes are used, then the oxazolone formation can be prevented, and that's why urethane protection groups are nowadays used for protecting the alpha amino group in amino acids. So now we discuss the transient protection groups of N-alpha amines. The name, now you may ask, why is there the name transient? Transient comes because usually when peptides are built up, the amino group gets removed, the protective group at the amino site gets deprotected in each step so that the next amino acid can be attached there, and that means transient means it is continuously cleaved during the peptide synthesis, while, for example, the protective groups that are needed for the side chains, they are kind of persistent or kind of permanent protective groups, because during the whole synthesis they remain on the polypeptide structure. They are only cleaved in the last step when the complete peptide is made. So there are more than 100 protective groups for amines for peptide synthesis. However, there is no universal protective groups, so we only discuss here the most important one, and one of the very famous one, and every chemist knows this, is the so-called Boc group, and Boc stands, this abbreviation stands for terz-butyl oxycarbonyl. Let's see first now how the Boc group can be introduced in the amino acid. That means, how can I protect an amino acid? That is shown in the scheme in the middle of the slide. We can, for example, start with compound 7, which is an azide, and this azide can selectively react with the amino group of the amino acid, and we form the Boc-protected amino acid. We can also start with the starting material 8, which is the Boc anhydride. The Boc anhydride again selectively reacts with the amine group of the amino acid. The Boc group is introduced to the amino acid, and under the extrusion of carbon dioxide and terz-butanol, the Boc-protected amino acid is formed. The characteristic of the Boc group is that it's stable against bases, and it is stable against hydrogenolysis. However, it is labeled against acids, for example, 3-fluoro, trifluoroacetic acid. That means during the synthesis of polypeptides, the Boc group is liberated from the amino group by the application of protons, and the mechanism how this works is shown at the bottom of the slides. So first, the carbonyl group within the carbamate structure is protonated. That leads to the formation of a terz-butyl cation, and it forms the carbamate structure shown on the top in the reaction scheme. The carbamate structure loses carbon dioxide further in the process, and the terz-butyl cation is transforming into terz-butylene, and the proton from the terz-butyl cation is migrating to the ammonium group, meaning it is protonating the amine. The terz-butyl cation is a reactive species. It is usually scavenged during the process by the addition, for example, of anisole, which is an electron-rich aromatic compound, and the terz-butyl cation usually undergoes electrophilic substitution with this aromatic compound, and therewith is removed from the reaction mixture and cannot react with the peptide chain. Another very important transient protection group of N-alpha amino groups is the Fmoc group, and Fmoc stands for 9-fluoronyl methoxycarbonyl. Again, the Fmoc group needs to be introduced to the amino acid. So the question is, how do we synthesize the protected amino acid? In this case, for example, fluoronyl methoxy carboxylic acid can be used. In this case, we have a chlorine in the position X, and this forms a formic acid chloride structure or a formyl chloride. In this case, we then achieve the Fmoc protected amine groups. In contrast to the Boc group that we have discussed before, the Fmoc group is stable against diluted acids, and it's not completely stable against hydrogenolysis, and it's labile against bases. So how is the Fmoc then protected, deprotected, once the peptide bond has already been achieved? This is usually done by adding piperidine to the reaction mixture, and the mechanism of removal of the Fmoc protective group usually starts by the piperidine removing a proton at the 9 position of the fluorane scaffold. In the next step, then carbon dioxide is in the next step, then the negative charge at the 9 position of the fluorane unit eliminates the oxygen of the formyl structure. In this case, now a double bond is formed at the 9 position, and the carbamate structure is obtained at the amine. In the last step, then the formyl structure is releasing carbon dioxide, and the piperidine is added or is undergoing an addition reaction to the double bond, while the free alpha amine group is obtained then after this basic treatment. It is important to note at this point that the Fmoc group is the most important protective group for N-alpha. So now let's go away from the transient protection groups and let's discuss the persistent protection groups, or the protection of the side chains. And again, there are multiple protection schemes depending on the synthesis strategy that is chosen for the polypeptides. I only want to discuss here the protection of the side chains when Fmoc group is used as the transient protective group of N-alpha. When Fmoc is used, then the cleavage of the transient protective group is afforded under basic conditions, and that means that the side chains need to be stable against bases, and therefore these side chain protective groups, they are acid labile as we see below. For protection of aspartate and glutamate, this is done, so the carboxylic acid group is protected with a t-butyl ester, the serine, threonine, and tyrosine, that means the amino acids that contain a hydroxy function, they are protected with a t-butyl ether. The lysines, which carry an amino group as the side chain, they are protected with Boc. We have already seen how the Boc group looks like. The same holds true for tryptophan and asparagine and glutamine. They are protected with 3-phenylmethan. The structure is shown right beside. Then the cysteine containing the thiols, they are protected with the same protective group, and histidines are also protected with triphenyl methanes. And a very complicated looking protective group is chosen for arginine. I don't read the name now from the slide, but this protective group is abbreviated PBF group, and the structure you can see again on the bottom right. So now we have solved all the problems of protection, and now I would like to come to the solution of the second problem that I have mentioned right in the beginning of my presentation, and this is the formation of the peptide bond. The most common reagent that is used to activate a carboxylic acid group is DCC, and DCC stands for dicyclohexyl carbodiamide. Once the carboxylic acid group reacts with DCC, it forms an O-acyl isourea compound, and in this case the carboxylic acid group is activated in such a way that nucleophilic attack of the second amino acid leads to the formation of the peptide bond. In this case, the dipeptide is shown, as you can see on the right hand side, and as a side product we have now formed dicyclohexyl urea, or DCU is the abbreviation. The dicyclohexyl urea is a compound that is very hard to remove out of reaction mixtures, and therefore another method has been introduced to form peptide bonds, and this variation of the carbodiamide method is the utilization of activated esters. In this case, again, we start with activating the amino acid with DCC, and instead of now directly adding the second amino acid, we, for example, add N-hydroxysuccinimide that you see at the bottom, and this NHS can react and replace the DCC. Now you have the big advantage that you can easily purify your activated ester. You get rid of the dicyclohexyl urea, so meaning you can start, or you can solve the problem of purifying your dipeptide from the dihexyl urea. You can solve this problem beforehand, and you don't need to do a difficult purification with your polypeptide reaction mixture. In this case, then you have the activated amino acid that can react with the amine group of the second amino acid, and you via this process you remove NHS again, and as a you have formed your desired product, which is the dipeptide. So activated esters, for activated ester formation, N-hydroxysuccinimide can be used as mentioned, and N-hydroxybenzotriazole are usually used. Additional advantages. An additional advantage is that NHS or HOBt are weak acids, and as we have learned before, a reaction medium that is slightly acidic leads to less racemization. So it's not only the big advantage of being able to solve the purification problem of removing dicyclohexylurea, you also solve the problem of racemization, or you at least have less racemization in your synthesis when you use these activated esters. There are also alternatives to DCC. One is diisopropyl carbodiamide as the activating reagent, or the water-soluble species EDC, the name of the compound you can read at the bottom of the slide. So now we come to a concept that changed dramatically the synthesis of polypeptides, and the concept that was introduced is the concept of solid phase synthesis. That means the peptide formation is not done in solution, but the peptide formation is done on a solid phase. So your polypeptide is growing amino acid by amino acid from a solid support. This concept has been introduced by Bruce Merrifield in 1963, and it was awarded, or this invention was awarded the Nobel Prize in 1984. The advantages of this new technique at that time compared to solution synthesis is that excess of reagents that can be used in this process leads to higher conversion and finally to higher yields. It is much easier when you work on a solid phase that the purification gets much easier, because you can just use a glass filter where you have your beads in that contain the peptides, and you can easily wash them and get rid of side products compared to when all the components are in solution. And finally, another advantage is that this process can be much easier automated than a solution synthesis. On the right diagram, we have now the different steps that are needed to perform the peptide synthesis on solid phase. Usually you start out with a polymer bead. On this polymer bead, you introduce a suitable anchor group, and onto this anchor group you attach the first amino acid via the carboxylic acid group, and then you have an N-protected amino acid on your solid support. What you need to do then is you need to remove the transient protection groups for N-alpha. You have then a free amine group, and this free amine group can then react with a appropriate protected amino acid that contains an activated carboxylic acid to form the dipeptide. And then steps 3 and 4 you need to so many times repeat until you have reached the desired peptide. Afterwards, you again cleave your N-alpha protection groups, and finally you need to introduce a cleavage step that cleaves all your side chain protecting groups, so the persistent protecting groups, and at the same time that cleaves your peptide material from the resin, so that you obtain the free or the pristine peptide. Merrifield got the Nobel Prize for his invention of solid state or solid phase synthesis. That's also why the strategy, or one strategy of making peptides on the solid phase, is named after him. Here I would like to discuss the Merrifield synthesis strategy with you. On the right-hand side, when you look at the scheme, you should imagine that there is a polymeric bead attached to the NH group that you see on the right-hand side. In this case, now there is a linker shown, and onto this linker, the first amino acid is already attached. Who sees what amino acid this is? If you look carefully and remember the first lecture about peptides and proteins, you can easily see that is serine, and the serine is protected as an ether in this case, and an alpha is protected with a Boc group. The Boc group is now cleaved from the amino group with trifluoroacetic acid. In the next step, then we obtain the ammonium N-terminus of our first amino acid. In the next step, then we add a base. The base removes the proton from the ammonium group. We form the amino group, and this amino group is now nucleophilic enough to attach or to react with the next amino acid. In this case, again, the question is what amino acid we have attached here. In this case, this is alanine, an alanine unit that had been introduced by using Boc-alanine anhydride, as you can see on the reaction arrow. Again, this group is protected with the Boc group, and if you now want to attach another amino acid, in the next step you need to remove the Boc group again to end up with your free amine to be able to attach the next amino acid. However, in this scheme this is not shown, so we directly go to the next steps. Again, first with TFA in dichloromethane, we remove the N-alpha transient protective group, and then the final step is in chemical terms speaking, a really ugly step, because you need HF in anisole. HF is a very, very strong acid, and it's very hazardous. You need special equipment. You cannot do it in glass flasks. So this is a kind of ugly step. It contains quite harmful reagents. So with the HF treatment, you remove all the side chain protective groups, and at the same time you cleave the ester bond with which the peptide is connected to your resin, and with this, in this case, you now liberate your desired dipeptide from the solid phase. Now I come to the second strategy that I would like to discuss with you. This is the Fmoc strategy, and the Fmoc strategy is nowadays the most important one that is carried out in most of the laboratories worldwide. The advantages of this method over the Merrifield synthesis scheme is that no toxic HF is needed. I told you on the last slide, this is really a kind of dangerous step, and the absorption of the fluorine unit can be exploited to determine the coupling efficiency, and this leads to better automation of the process. Again, I would like to discuss this particular synthesis scheme with you. Again, like on the slide before, in your imagination, you need to put a polymer bead to the very right of your scheme. Onto the polymer bead, you have amino group, and this amino group is connected to a linker system. This linker system is now again attached to a Fmoc protected serine group. The hydroxy group of the side chain of the serine is protected as a butyl, as a terz-butyl ether, as we have already seen. That is the persistent protective group that is used in this case. Now we use piperidine in DMF, so we choose a basic treatment to remove the Fmoc group. We directly obtain the amino group, the alpha amino group, that can readily react with the next Fmoc protected amino acid in the presence of HBTU and an amine and the base. In this case, now we form the same peptide as discussed in the previous synthesis. Again, the peptide is now protected with a N-terminal Fmoc group, and this again, if you want to extend your peptide chain, would need to be removed by piperidine. However, again, we now stop at the level of a dipeptide, and now we cleave with piperidine the N-alpha in the last step. And important now, the really last step of the synthesis now doesn't involve the toxic HF, but just involves 3-fluoroacetic acid, which is by far not as dangerous as the HF. And by this TFA treatment, you cleave all your protective groups of the side chains, and you can cleave your peptide material, in this case the dipeptide, from your resin. Let's have a look at the solid supports that are used in solid phase peptide synthesis. These polymeric beads, they must show a good swelling behavior, and they must be chemically and mechanically stable. The good swelling behavior you can understand as such that once the polymer beads are exposed to a solvent, they increase in size, and this increase in size is needed so that during the synthesis, the reagents can reach the immobilized growing peptide chain during the synthesis. And the larger this swelling factor is, that means the size increase, the better this reagent can access the growing peptide chains. The formation of beads is usually obtained by using a cross-linker. That means the polymeric chains, in this case mostly polystyrene, they are the polystyrene chains are connected together so that they are not just dissolve and they go towards a synthesis in solution. So the peptide chains, they get connected by around 1% application of divinylbenzene that connects all the chains together so that the material can swell but not dissolve in the reaction mixture. Then we also need to discuss a few linker systems that are usually used. The linker, they serve as a protective group of the carboxylic acid C-terminus. The selection of the linker allows to determine the functionality at the C-terminus, for example, whether you want to obtain the carboxylic acid or if you want to obtain there an amide. Let's start again with historically with the Merrifield resin. The Merrifield resin you see as the first example. Here cleavage is achieved by strong acids. You have learned what a strong acid is. In this case it was HF. For the Fmoc or for the Fmoc strategy, usually Wang resins are used. They are more labile towards acid compared to the Merrifield resins. They are stable against bases, and cleavage is usually obtained by 90% trifluoroacetic acid. Now you can see with the introduction of a small methoxy group and increasing the electron density in your aromatic system, as realized in Sasrin resins, you get the resin more labile towards acids compared to the Wang resin. Again, this linker is stable against bases. It's employed again in the Fmoc strategy, and now you don't need 95% TFA as in the Wang resin, but you can cleave your material from the resin just with 0.5 to 1% TFA solution. And finally, the ring amide resins, they have been introduced so that after cleavage of your peptide from the solid support, you don't end up with a, so to say, naked carboxylic acid at the terminus, but that you introduce there an amide. And this, for example, helps when stabilizing peptides in biological media. Once there is an amide at the C terminus, then they can be, or they are proteolytically more stable than the pristine carboxylic acid. With this slide, I would like to demonstrate you that the coupling step of each individual coupling during peptide synthesis is very important when you do this on the solid phase. The table is built up like that in the first row you have the yields obtained for individual coupling steps. They are given in percent, and if you look if in all your coupling, when all your coupling yields of individual reactions are 99%, if you have a 10 mer, your overall yield is 90%. If you synthesize a 20 mer, keep in mind with 99% reaction yield of the individual steps, when a 20 mer, you're only at 80% yield. If you make a 50 mer, then you end up with 61%. If the coupling yield of each individual step drops to 95%, already at a 10 mer, you only get 60%, and if you synthesize a 50 mer, you almost end up with almost nothing. And what you also see that once your coupling yield reaches 90%, that your yield already higher than a 20 mer is meaningless. So the coupling efficiency is a very important point. And nowadays, the peptides that can be achieved using these synthesis schemes that I have just introduced to you is around 40 amino acids that can be synthesized in specialized labs. The solid phase synthesis compared to using, for example, nature to produce, or biological processes to produce peptides, offers great opportunities. You can, for example, incorporate non-natural amino acid. You can, for example, incorporate not L but D amino acids. You can modify peptides with reporter units, like, for example, fluorescent dyes. You can put modifications in the backbone, so you can, for example, make it more stable against proteolysis. And you can introduce also artificial post-transcriptional modification. For example, if you think about phosphorylation, which is important in signal transduction, or you can put sugar units on proteins, which is not so easy in some expression hosts when you choose the biological synthesis pathways, or you can introduce lipids, which is also a post-translational modification Mother Nature uses to equip some proteins with lipid to give them a special function. Solid phase peptide synthesis is extremely important for pharmaceutical industry. Therefore, I've shown here the slide that you see. I don't want to go into too much detail. I just want to give you an overview, and what you see from this summary is that solution phase synthesis is a viable method to synthesize peptides. Recombinant synthesis is also a viable method to get to different structures, and it's becoming more and more important. So this is a relatively old overview, so it should be taken with care. But at least at that time, solid phase synthesis was very important, as you see by the many crosses for the different peptides that are that have medical relevance. A lot of these peptides have been achieved by solid phase synthesis. With this, I'm at the end of my presentation. I thank you very much for your attention, and I hope you have learned how you can build up synthetic peptides and using solid phase synthesis, and probably also the machines that are made the solid phase peptide synthesizers with which this can be performed. Thank you very much.